We already know that there's a relationship between pressure, volume, and temperature. Now, with Avogadro's law, we can see that there's also a relationship with the number of molecules. So this modifies the gas law a little bit. P1V1 over N1T1 is P2V2 over N2T2. N is the number of moles of gas. And that constant has a specific letter that we use the letter R for the ideal gas law constant. The image on the side is showing that if they're at the same temperature and pressure, they have to have the same number of molecules, even if they're different gases. By rearranging that equation for a single set of conditions, we can come up with the ideal gas law. And ideal gases have to follow the postulates of the kinetic molecular theory. There are no interactive forces. Molecules have essentially zero volume. The total energy is conserved at all times. So let's take a look at this, and here are our variables. Note that temperature still has to be in Kelvin. You cannot use degrees Celsius. R is a constant, and the numerical value depends on the units of pressure, volume, or pressure and volume, because temperature has to be in Kelvin. So how do you know what to use when? When you make a chart, the variables will tell you whether or not you use the ideal gas law or the combined gas law. And the pressure units let you know which value of R you're going to use. Most of the time, we will use 0.0821 liter atmospheres per mole Kelvin or 62.4 millimeters of mercury, or torr, liters per mole Kelvin. Note this entire thing is the unit. So there's only one gas law constant. Numerically, it changes depending on the unit. The analogy I have here is, let's take a look at this line. It only has one length. But whether it measures 11.49 centimeters or 4 7/16 inches depends on the units we're using. In the same way, 62.4 works for millimeters of mercury, 0.0821 works for atmospheres. So let's try some of these.